in New York. Okay, so. Okay. The last time I gave a seminar here was during COVID, and that is was an online meeting, and that is no fun. But it is a remarkable difference because when to give that seminar, I just said goodbye to my wife, went to the upper floor, to the computer, and I gave the seminar. And an hour later, I came back. And now I fly to New York. You stay here and you go back. But it's much more fun to see people. So I really like it. And so I would like to talk about work, which I should say is still work in progress. But it's about the consistency, the existence of a consistent limit of 11-dimensional supergravity. So it's a limit which leads to a much smaller theory, which is self-consistent in itself. And I did this in work in collaboration with Chris Blair, who is now in Madrid, a postdoc, and Johannes Langsteiner, who started a postdoc in Stockholm, and Jan Passil, who's in Zagreb. So it sounds like a supergravity talk, but the motivation is really from string theory. And let me see just a second.
Try again. It should work now. Sorry.
Maybe it's not.
No, you go to the next page. It's already the first page.
Okay, so let me a bit history, and it's just to give you the motivation. Is that we all know about the relation between D-branes and Mills-Gates theories, but 20 years ago there was a development where people noticed that there was a funny limit if you took open strings with a critical electric field. Then that led to a so-called they called it non-commutative open strings. That led to a non-commutative field theory, where the closed strings decoupled and it became a kind of nice non-commutative theory. That was with a non-commutativity between space and time. So there was some development here. But then it was noted by Klebanov and Molesena that although the closed strings decoupled here, that if you would take a compact direction, then they didn't decouple. And then later it was realized by Daniels, Nettel, and Gomez-Okuri, that if you could even omit the D-branes, and then you are really left with a theory of what turned out to be non-relativistic closed superstrings with a non-critical critical B field. And so these groups, they really took that as a starting point, that they tried to define a non-relativistic version of closed superstring theory, whose low energy limit is supposed to be supergravity in 10 dimensions. And recently, we showed how indeed there is a limit which makes this into a non-relativistic theory, which is then the beta function calculation could show it was really related to the low energy limit of these closed superstrings. And around the same time, 20 years ago, people tried to uplift these remarks about string theory to M theory, where they considered open membranes, then critical free-form field, and that led then towards what's called a non-commutative open membrane theory. And then it's in the same way as here, the closed strings didn't decouple if you were considering wound strings. There was a work at that time which shows that if you look to closed supermembranes, wrapped supermembranes, that they didn't decouple, but with the condition that was a critical free-form field. And that is then supposed, this is of course less well defined, there's no sigma model, it's all non-perturbative, but the idea is then that suggests that there should be a consistent limit of 11-dimensional supergravity. And what I will show in this talk, so this is just a kind of motivation and history which already happened 20 years ago, that indeed, if you take 11-dimensional supergravity, there is a limit which is consistent and shows that there's a little theory hidden in 11-dimensional supergravity. And this limit is a so-called non-relativistic limit, but it's very subtle. If it would be just a matter of take the limit and go home, that would not be interesting. The issue is that you get continuously plagued with infinities, divergences, and the theory really has to take care of these divergences. And that's the story of my talk, how you can take care in an unexpected way. If you would not believe in this limit, you would never do it. But I will show you all kinds of tricks that all these divergences disappeared, and we are left with a very small new multiplet, which is consistent with these expectations.
Eric, can I ask a question? Just as a question about the history part. So, in the string theory case, what is the Walshy CFT precisely?
So these are open strings and non-D-brane. So
no, but in the closed string, like
in the closed strings, it's That it's a relativistic world sheet. Just
know,
so
yeah.
in the Gomes and Guri,
Yeah.
they take a stop. So although you call it a non-relativistic string, it's non-relativistic in the target space.
That's what I meant.
But
What
it's
is target space?
Yeah, but it's relativistic in the string, and
Yes.
you do that because otherwise you can't do any calculations.
Yes, yes.
There are people also who take that even non-relativistic, but then you get weird exotic things
Yeah,
which
so
I cannot use as a starting point.
Yeah, so I know it's a relativistic worldsheet CFT.
Yeah.
I'm asking what that CFT is, if it's an exact CFT with a non-trivial detail.
Yeah, I think so. If you look to the paper by Gomes and Guri, then they write down explicitly the sigma model and they quantize it literally, and it all seems to be lead to it is I would say a non-relativistic conformal field theory. Yeah.
I'm asking if there's a kind of more complete characterization of what that CFT is.
Well, I don't think there's much work on that.
Is it related to some deformation of WCW models? Or
well, it's sometimes they relate to TT bar deformations or something, but there's not much work on that, I must say. The only one which these people did is they did the obvious thing. They took what they did, in fact, they took the Polykov string. This is a known sigma model with a known CFT, and they literally took a critical limit of that model. That's what they did. So they show how it's related to the Polykov model.
Yeah.
And it's a critical limit because we will see that there are again also there divergences which you have to cancel. So, and so it's really a limit in that sense of the Polykov model.
I see. But there's no exact
target space relativistic invariance is important for choice of critical dimension. The relativistic invariant in target space, Lorentz group, or Poincare group, basically determines what is a critical dimension. Right? When we teach the critical dimension 26 or 10 or something, we use the target space Poincare invariant. If you break target space Poincare invariant, if you remove it, I don't think critical dimension has to be 10.
Well, no, they calculated this goes good. They calculated that the critical dimension remains 10, but it really changes. It's not an obvious limit. They use a trick, which will also occur in my talk, where you get extra ghost fields on the world sheet, beta gamma systems, and then they calculate the critical dimension, and you really get 10. This is also reasonable. If you take the limit of a relativistic string theory, you expect to get a 10-dimensional string theory. But they show that doesn't change. So, and that's also why and by the way, also these beta function calculations have been done. So you really can show that if you take that sigma model, you get really the equations of motions of this theory.
I would think that from target space point of view, it's just a different background. Suppose you have a description of target space theory which is background independent. Okay, just like that. Then you pick the b not equal to 0 and expand it around b not equal 0, and of course you will think that it is not relativistic anymore, because turning on any b field would pick some directions. It's similar to non-commutative Young-Mills for open strings, when it is same theory but expanded around constant f, constant electric field or magnetic field. It's same theory, different background.
Well, I will come back to exactly the discussion you have. I call it now non-relativistic string theory, but the question is I will address at the end, in which sense is it non-relativistic? I will come back to this question. But for the moment, that's how everybody calls it, the naive spectrum, everything is non-relativistic. So, but the point I want to do is that to show that how by all kinds of subtle means, you can indeed take this limit of 11-dimensional supergravity. And so the organization of this talk is, first of all, you have to use now the string propagates now in a non-relativistic geometry, not a standard Riemannian geometry, and it has to be adapted to the membrane, so I call it the membrane Newtonian geometry. And then I'll show, using that geometry, how the limit can be taken, and at the end, I'll then discuss some generalizations and open issues. So first, some geometric remarks. So in general, forget about membranes, take a particle. How do you take a non-relativistic limit of a particle, coupled to generativity, is that you take the Vierbein fields of generativity, you split them in time and space, these are called the clock and the rulers, and you, like in Wittgensteinian contraction, you redefine the fields. That's just relativistic, a redefinition, but the fields at the right hand side, they will become the non-relativistic fields after you take the limit omega to infinity. So it's really not quite an expansion. I take a limit is kind of an invertible redefinition followed by a limit like a Wittgensteinian contraction. The remarkable thing is that it only works if you add an extra vector field for massive particles and you expand it like this way, and that is because, you see, if you go from a relativistic to a non-relativistic theory, there's really a big difference, because in the relativistic theory, energy is conserved, but in the non-relativistic one, energy and mass are separately two conserved things. So you have two neutral currents in some sense, and so you really need, and also at the algebraic level, if you don't go from a Poincare to a Galilei algebra, but you will go from a Poincare to a Bartman algebra, which has a central extension, and this M really represents this, basically this extra M here represents the central extension of the Galilei algebra. And then, so this, everything's still relativistic, it's just going to a different basis, and then you take the limit, the omega to infinity, but already, and then you take care of, that's the point, if you take the limit, you get all kinds of divergences, and we have to take control of them. That's the theme of this story. And you already see that if you just take this particle coupled to general relativity, then if you write down the kinetic term of that particle, and you just take this redefinition, then that blows up, you get an infinity. And the way to cancel it is then that you add also a Wesso-Meinong term, you couple this M also to the particle, and then that's why this thing here also blows up. Then this divergence coming from this term cancels the divergence coming to that term, and this M is just then a field that couples to the non-relativistic particle. And notably also that because of this divergence, this M starts transforming the boost, it really becomes a geometric field. It's as important as the clock and the ruler. This is extra M, and you really need that Wesso-Meinong term to have an action which is boost invariant. If you write down a non-relativistic particle in a curved background, then the kinetic term by itself is not good enough. It's not boost invariant, but with the Wesso-Meinong term, it's boost invariant. So this M is as important as the clock and the rulers. Now, if you now take the limit of general relativity, then an issue arises, because if you do again these redefinitions, you take omega to infinity, then you can't do it in the Einstein-Hilbert action if you use a second order formalism, because that leads to a leading divergence in the action. You expand the action, there's a leading divergence, and that can be tamed by assuming that you don't want to change the relativity, so you take the curvature of M to be 0. It doesn't represent a new degree of freedom. And if you do that and you take the limit, then you can control this divergence. But the price to be paid is that by hand, effectively you have to impose that the divergence of the curl of the clock function is 0. And this is called a zero torsion condition. If you do that, you can't write down an action now because this doesn't follow from action, but you can take the limit then in equations of motion, and then you get what is called the equations of motions of Newton-Newtonian gravity. That's the limit of general relativity without further assumptions. So it's more, Newtonian gravity is only valid in a restricted set of frames, namely the ones which are attached to the Earth with constant acceleration. This has much more fields, but it's valid in any frame, and it involves also strong gravity effects. But you have to impose this constraint. And what we'll see in this talk with when we take the limits of these supergravity theories, that we can avoid this constraint if we add matter to the Einstein-Hilbert action. That's one of the things we'll see. Now, and so if you take the limit in the equations of motions, you get as many equations of motions as the Einstein equations. So there is this represents the curvature of the boost and the curvature of the spatial rotations, and this is this extra constraint. And you can this mu index you can decompose in a time and a spatial. The boldface is a spatial one. This represents one condition. This is then other conditions where B represents a spatial index, and these, if you add it up, is exactly the Einstein equations. So it's not quite that space has to be flat. So there is a paper where people look also to realization of Newtonian gravity with curved spaces. But in the supersymmetric case, we often will see that we have to take space flat, but not space-time. So this RG remains non-zero. And in fact, that is the one who will contain the Newton potential. And this is a singlet, and that's really the Poisson equation. So if you assume flat space, so a kind of special solution, and after gauge fixing, you'll see that so this contains many fields, clocks, rulers, and this mu, but many components can be set to 0 or delta functions, and the only thing that survives is then the Newton potential, and this equation represents then Laplacian phi 0. I've added no source terms, and basically this Newtonian potential can be identified with the time component of this extra vector field we added to general relativity. That is the Newton potential. Now, so that's how it goes. But what plays an important role in this talk is that we have imposed a constraint, and this is what I call a geometric constraint. The special thing about this constraint is the curl of let's say a vierbein, but it doesn't contain a spin connection. So it's independent of the spin connection. That doesn't happen in general relativity. The reason being is that this would be the time component of the vierbein, and that would transform on the boost to the ruler. But if you take the limit, then the clock of Newtonian gravity is invariant on the boost, and that's why this exists. So the presence of these strings without spin connections, that's very special for degenerate geometries and this non-relativistic geometries. It doesn't happen in relativity. So it enables you to impose constraints on the geometry. And in this case, it's an attractive one because it tells you that tau is a derivative of something. And then if you use that, you can show that if I represent a Newtonian, so this in fact defines a Newtonian space-time. So if you divide the universe into slices of equal time events, and an observer would travel from one slice of bread to the other slice of bread in different paths, that two observers in different paths, they would agree about the time difference, because they would measure the time difference using the clock function. But in the presence of this constraint, the clock function is a total derivative, so it only depends on the endpoints of the curve, it's path independent. And that's the definition of absolute time. And so this term is often called torsion, this curl, because if you write out the metric postulate for this clock function, you'll see that the antisymmetric part of the affine connection contains the curl of tau. So it's not an independent, in relativity you can also add torsion tensors and independent tensors, but in this case, you can't take this thing to zero, that would impose this constraint. So this is often called either a geometric tensor or an intrinsic tensor. And these guys, they play an important role in the discussion to follow, because they enable you to impose gauge invariant constraints on the geometry, constraints which you cannot do in relativity. Now, so I want to, but to go to the membrane, I have to do a similar thing, but slightly different. I will include also matter, because we know that the membrane couples to a 3-form, and that will play an important role. I will use that in taking the limit, and I will extend that. So that will place, in fact, my vector field, and I will extend it in this way. And I need, for instance, if you look to now not a particle coupled to relativity, but a membrane coupled to relativity, the kinetic term again blows up, but much more because it's a volume, and that has to be cancelled by coupling this free form to the membrane, which again has a divergent term. You can't couple a vector to the membrane, as in the previous case. So you have to go in 3 form, but that requires, to write this down, I need 3 tau functions, which I call now longitudinal vierbeinen. Otherwise, this is antisymmetric, this would not exist. So what I do is I change the foliation of space-time. Instead of dividing it up in time and the transverse directions to the particle, I divide it up now into the 3 directions longitudinal to the membrane and the rest transverse to the particle. That's why we call it a codimension 3 foliation. So instead of 1 tau, I have 3 taus and less rulers. And then everything goes very similar. So it's just a matter of changing the dimensions of the foliation. But after taking the limit, then this C remains in the non-relativistic theory and becomes again a geometric field, which will be as important as the vierbeins. So, and you can check that in the bosonic membrane model, that if you do these redefinitions for the clocks and the rulers and for the C, there's again a cancellation between the kinetic term of the membrane and the Wesenminute term. And there you get a sigma model for a non-relativistic membrane. So the variables of, so if I take the limit of 11-dimensional supergravity, I want to get what not Newton-Cartan gravity, but let's call it membrane Newton-Cartan gravity. It's a different version. So I will not, instead of the vierbeinen and this extra vector field, which is the clock, the ruler, and the central charge gauge field, I will do a membrane redefinition. I will split the relativistic vierbeinen of 11-dimensional supergravity into 3 longitudinal vierbeinen, and the rest are transverse vierbeinen, and this C, I do the redefinition I showed on the previous trapezoid, gives this 3 form. And the Newton potential will be identified with the world volume component C012 of the 3-form gauge field. Because if you take this membrane limit, that's how this one couples then to the membrane, that's the Newton potential. And after gauge fixing, this guy is supposed to be then the Poisson equation in the transverse, in the transverse directions. So it is a kind of variant of Newton-Cartan geometry, but now adapted to membranes. I really do a membrane redefinition. Yeah, and this redefinition I want to do for 11-dimensional supergravity, and then see what happens. Now remember, for relativity, when I took the Einstein-Hilbert term, I took the limit, already blew up, but then this vector field I had, I didn't really consider as an extra matter field. I tried to kill it. I set the curvature to 0. That vector field is really related to the Noether symmetry of the conservation of particles minus antiparticles. In this case, the free form plays a different role. It's really part of 11-dimensional supergravity. It has a kinetic term, and that plays an important role. So that's all I do. I take this redefinition, it's a slight extension of Newton-Newton gravity, and I try to plug it in 11-dimensional supergravity because I think a limit should exist, and let's see what happens. So that's what I'm going to do. So I take first I do the bosonic case. I take the action of 11-dimensional supergravity. This is the Einstein-Hilbert term. This is the 4-form curve to the 3-form, and there is an extra Chern-Simons term in 11-dimensional supergravity. I do the redefinition. I split the relativistic flat index into 3 longitudinal directions longitudinal to the membrane, and the rest is the 8 transverse directions. You do the redefinition of the vierbeine, like I did before, and the 3-form, so that in the bosonic membrane sigma model is a cancellation. And now what you find is that if you expand the action, I don't take yet the limit, this is just a redefinition, you get an omega cube divergence, a finite term, and a term is sublime, which if I take omega to infinity will disappear. So here you see the divergence which happened also in relativity. That's why there's an issue. But now I just leave it as it is because now I have this, you see the difference is that now I take this 3-form seriously and I add also, not only have an Einstein-Hilbert term, but also have a kinetic term for the 3-form field. And then what you see is that because we take really a critical limit, in the same way if there was a cancellation between the kinetic term and the Weber-Miller term in the sigma model of the membrane, you find that's somehow reasonable that there's also a cancellation between the infinity coming from the Einstein-Hilbert term and infinity coming from the kinetic term for the 3-form. At least that 3-form kinetic term gives 2 types of divergences, but one of them cancels against the Einstein-Hilbert term. So I can take the limit now in the action, there's a cancellation, and their contribution to this S3 precisely cancel. But there is still, this 3-form gives one more divergence, and I'll discuss that in a minute. But there's one more thing that happens, is that once you take the limit, the action is invariant under an emerging local anisotropic dilatations. It's anisotropic in the sense that only the taus they transform into dilatations, but not the transverse vierbeine. And that's not so deep, that really has to do with the fact that you see it also in the sigma model. The fact that it happens is that, I mean, usually we know that we always say the string is invariant under dilatations and membrane not. That makes the membrane more difficult to study. But these are always isotropic dilatations. Here I allow anisotropic dilatations, and then any extended object has this. The only special thing for the string is that the taus transform into dilatation and the transverse will not, and here both transform. So this is just an invariant, but that means that you lose a field. If in this non-relativistic sigma model of the membrane, you lose, and in this action, if you have local dilatations, there's a field missing. And what I say now is not really important for the thing to study, but I just want to stress that the action we have is not given full information, because you miss now a field and hence an equation of motion, and I will show you how it sorts it out, but it's just a technical remark, and we will not really need it much in the following. But the point is that due to the dilatation symmetry, after taking the limit, there is a missing equation of motion, whereas all the other ones, I call it M, all the remaining equations of motion, which I call R, they follow from the non-relativistic action. And if you want to get this missing equation of motion, what you really should do is you should not take the limit in the action, but you should first vary the action, you get the equations of motions, and then you take the limit of the relativistic equations of motion. And then you find that the missing equation turns out just to be the Poisson equation of the Newton. The guy should give you the Poisson equation of the Newton potential. And in some sense it makes sense because there's a kind of folklore saying that there is no action principle for Newton-Newton gravity unless you really play around with new symmetries. And that's why if this would not happen, then we would have an action principle for Newton-Newton gravity, and that's not to be expected. And what it really means is that if you look to the full set of equations of motions, then you have this the remaining equations that follow from this action. Well, action it's an auxiliary action, I would say, and there's a missing equation of motion. But it's not that the missing equation doesn't need S0, they together form what's called a reducible but undecomposable representation. And that's it is often what happens in non-relativistic booster representation. So what you have is that the equations of motion that follow from the action, they transform under boost to each other, because that's usually if an action has a symmetry, the equations of motions transform to each other. They don't transform to this Poisson equation, but the other way around, the Poisson equation is not boost invariant, but under boost it does transform to the equations and motions of this action. So it's like a boost. Eh? If you boost space goes to time, but time doesn't go to space. It's kind of half a rotation. That's what they call a reducible decomposable state. That's here also what happens. So one equation, this m goes to r doesn't go back to m. So, and that's how it belongs to each other. And then you have all the information. So strictly speaking, you better take the limit of the equations and motions, but this action is still very useful because it summarizes all equations and motions but one, and we know how to get that one. So I would still call it the action, but you should more see it as a convenient bookkeeping device. Now, then there is a problem, there's a problem characteristic for the Ramon-Ramon sector, which has this Chern-Simons storm, because this kinetic term of the three form gives one more divergence, which is different from the Einstein-Hilbert term. And also the Chern-Simons term blows up, but now something nice happens. So, and they don't cancel, but something special happens. And so it really requires a fine tuning of the 11-dimensional supergravity coefficients. If you would not use these coefficients, it would not happen. But it turns out that the divergence is proportional to the curvature of the three form, but the whole thing combines into an exact square of the cell dual, of the SO8 cell dual part of this curvature. And the important thing is it's a square of something. And now it's a little trick that you can tame this divergence by what you do is that you first rewrite the Lagrangian by introducing an auxiliary field lambda. So this happens for every x, where x is now this f plus. If you have a divergence, then this thing is equivalent to this guy, where lambda is an auxiliary field. Because you can show, if you solve for lambda, then and substitute back, you get this. And after you take the limit, then this term disappears, and then the auxiliary field becomes a Lagrange multiplier. And then, then you can take the limit, and so now there's no omega cube divergence anymore. And then you take the limit and lambda, so you get an extra Lagrange multiplier. And in this case, this Lagrange multiplier is a cell dual SO8 thing. You could, I didn't check the details, so I'm sure you could avoid this kind of trick if you would take the limit not in a Lagrange formulation of 11-dimensional gravity, but in a Hamiltonian first order formulation. Then you could avoid this trick. But if you don't do that, and this, by the way, is a trick which was also applied in the original paper by Gomez-Oguri when they took the limit of the Polyakov action. And then it's slightly different, but this extra field, that becomes this extra beta gamma system they have to add on the world sheet. So you have an extra beta gamma system, but they get again an infinity, they solve it by this trick, and then they really needed then to get all these critical dimensions, etc. Right. So there's an extra beta gamma system in that case. So
really
now,
I think that it's not really a divergence, because if omega goes, I mean that term omega cube f square, right?
Yeah, that's divergence.
It gives in the path integral contribution only if f equals 0. So it's the same thing.
Well, no, this is but this is an expansion. Eh? This is part of a more of a bigger
an exponent, right?
It's still exponent.
It's an exponent of minus w cube.
Yeah, plus more terms.
Squared.
Plus more terms, because I've not yet taken the limit, and this was just a redefinition. I've not yet
Now,
taken
when
the
you
limit.
take the limit, omega goes to infinity, then the contribution comes only from f equals 0. In path integral, it's like infinite mass.
But then I can control almost every
That's what you get anyway.
Well, but now but probably you get then because I get my Lagrange multiplier is of course saying f is 0. So
right.
yeah, it's yeah.
Same thing. It's
Okay.
like
No, I'm not. I mean, I'm not proud on this.
No. What I mean is that
yeah.
when you introduce the Lagrange multiplier, you might start thinking at some point that it's a complicated thing to prove, that it's not dynamical, and because of the interactions and then the expansion. But it's easier just say that we take this omega goes to 0 limit, or infinity, sorry, and only f equals 0 contributes. But now you have other problem, which is f equals 0 is a constraint, which in this case gives you self-dual around the self-dual guys. It's very hard to.
Yeah, but be careful. I get many more constraints, and of course the dangers of a constraint is that it has to be evaluated in a supersymmetry.
Right.
And what's happening?
Yeah.
But my talk's not yet over. Eh? So be careful. No, I need this effect. Okay. So I'm not afraid for constraints. Oh. I should say, by the way, this, because we took also the limit of 10-dimensional supergravity, this is a typical complication for the Ramon-Ramon sector. This doesn't happen in 10 dimensions, because this whole Chern-Simons term is not there, and then this whole issue doesn't arise. We again find certain constraints for another reason, I will explain, but then they are automatically invariant in the supersymmetry, and there's no problem. But here, this is really particular for the Ramon sector. I have an F, I realize it's not invariant to supersymmetry, but I'm going to introduce yet more constraints, and they're all not invariant to supersymmetry. But we will come back to that. And of course, the danger is that it would kill the whole theory. That is, if you impose constraints, you have to be careful. But don't forget, it's not anymore. Well, we will come back to it. So. Because I still have to introduce fermions, and then so I had two types of divergence, and cancelling divergence between the Einstein-Hilbert and the kinetic term, and this Lagrange multiply thing between just sinus and the kinetic term of the three form. I want to add now fermions, but then the point is that these cancellations, more or less in the supersymmetric case, will go through in the action. That's not the problem, but now comes the horrible nightmare that we also get infinities in the supersymmetry transformation rules. That's where the extra complication arises. And to solve that, I have to say something about the difference between conventional versus geometric tensors. So remember, already in Newtonian gravity, I had this curl of tau 0, and that was something I could impose as a constraint because they had no spin connection. So I take all the curvatures of the vierbeinen and this freeform, because that's also in geometric field. So you need, and I divide it into, I take the curl, and I take projections, components of these curvatures, project to space longitudinal transverse directions. And if such a projection does contain a spin connection or a dilatation gauge, because there's also dilatation symmetries, then you see this is not I'm going to set this to 0, but what it will lead to is just it will solve for the spin connection in terms of all the other geometric fields. That's what we call in supergravity a conventional constraint. So the moment a curvature contains a spin connection, if you set that curvature to 0, then the constraint disappears. It's not there anymore, but you use it to solve for the spin connection in terms of the other fields. It becomes a dependent field. So with that, you have solved the constraint, it's not there anymore. So, but of course, this you cannot do, and that's new, if you have a curvature component where the spin connection does not occur, because then it's really a geometric, that's like the curl of tau, and that you can use to impose constraints on the geometry. Now, if you do this now for these curvatures, in this case, then it turns out that the following projections do not contain spin connections or dilatation gauge fields. So T is the curvature of tau, and F is the curvature of C. And the curvature of E has no geometric tensors. And the curly beams are symmetric tracers. So these guys do not contain spin connections. So you setting them to 0 constraints on the geometry, and all the other components I set anyhow to 0 because I use it to solve for the spin connections. And note that I've split my curved index into a flat and a longitudinal transverse part by using this inverse vierbeinen. You can do that. You can split so that's here I have all flat indices. So and everything is then projected to either longitudinal or transverse. Now, and remember that because that I will need, because that tells you we are going to get infinities in the supersymmetry rules. Now, but so now we take limits also from for fermions because we have supersymmetry. So and then you have to do a little. If you have a fermion, this is a little technical thing. You cannot just straight take the limit of a fermion because it transforms under spatial rotation and boost in a different way. You also have to redefine the parameters, and then it just doesn't work. So what you have to do is you have to split the fermion into two chirality projections, worldsheet chirality projections I define here. So I get two different projections. And then the trick is that you redefine the gravitino now with different powers for the different projections. And then if you take the limit and you calculate how it transforms in the boost, it becomes exactly, again, a reducible but undecomposable representation. That is that one chirality is invariant in the boost and the other one goes back to the first one. That's exactly what a boost always does. So, and this only happens nicely if you do it in this way. So it's a technical thing, but that's the way we take the limit of the supersymmetry of all the fermions and supersymmetry parameters, etc. So now first we look to the action in supergravity. That goes rather nice. But so you get again a cancellation between the divergences from the Einstein-Hilbert term and the kinetic term of the three form. That happens to hold continue in the presence of fermions. And this little trick which I did, all what happens is that the curvature of the three form becomes a supercovariant curvature. And the Lagrange multiply, this becomes supercovariant, and that's all. And I have now an action, if I rewrite like that with now, so with S3 is 0, no third order divergences. But now comes the disaster, because if I take the same limit in the supersymmetry rules, then there are again infinities, and that's bad because how do I get rid of them? Well, there are two types. There's first a special divergence, and that is a kind of cheating one because it's a divergence where it contains a divergence, this term, but you see, this term you could shift away by if you redefine your supersymmetry with an equation of motion. I can, because the equation of motion of lambda is this, and this term I can always write as an equation of motion plus a final term that the gravity goes to lambda instead of omega cube f hat. And the same thing you can do in the supersymmetry rule of the Lagrange multiplier, because that you can also shift by changing it in the equation motion of the gravitino. And that shifting is really an example of sometimes what's called a trivial symmetry. You see, any action, if you have, let's say any action with an A and a B, has always a trivial symmetry that you shift A with the equation of motion of B and B back to minus the equation of motion of A. Then that action is invariant. So you can always redefine your supersymmetry by doing that. So this divergence takes the form of a field-dependent trivial symmetry, and you could as well shift it away. But that's okay, but the problem is that there are more divergences in the supersymmetry rule. Omega, and I call it now the Q supersymmetry rule. And so we just find, if we take the limit, it's not our choice, but you find more omega cube divergent terms in the Q supersymmetry rule and the Lagrange multiplier. But the point is now, we already have shown that there are no divergences in the action. So how can it be that the supersymmetry rule has omega cube divergent terms, but if I substitute it, I found this is zero. So somehow these two things have to be cancelled. And if you think about it and you look at the details, then it turns out that the reason that it happens is that the action is going, this action S0 is going to have, like it had an emergent local gate symmetry, is going to have an emergent superconformal Stuckelberg symmetry, which guarantees that the fact that all these infinities that happen here occur as a field-dependent Stuckelberg symmetry. And it's like in conformal supergravity, where dilatations, the supersymmetric partner is an S supersymmetry, we call it a superconformal symmetry. And so that's the way it goes. So the theory becomes a bit smaller also. Eh? Not only we lose now one field by dilatations, but we also lose some fermions by these extra emerging Stuckelberg symmetries. And a nice check is that the commutator still is too close. Like in conformal supergravity, if you take a Q and an S, anti-commutator should give the dilatations. I know already how my fields transform into dilatations, and that exactly works. And that explains why if you vary S0, there are no divergences. But that's not enough. You have to be very careful in this expansion, because you also have a subleading term, and if you take then these divergent terms, it gives an extra contribution to S0. But you don't want that, because you want S0 only to be invariant under the zero order supersymmetry rules, and not a contribution from the subleading term. And that requires us to set some of the geometric tensors. In fact, all of these geometric tensors are defined, you have to set to zero. This one is not necessary, because that was an equation of motion. So it only works. And that also we found in 10 dimensions. The only difference is that in 10 dimensions, we found only some geometric tensor has to be zero. And then, happily enough, they turn out to be invariant on the supersymmetry. So we could go home. Here we have NS2 supersymmetry. There are more geometric tensors we have to set to zero, and they are not invariant on the supersymmetry. So we cannot go home. So, but they will lead to new constraints. And the question is, what happens? Because we have to face this fact. Well, it's clear that a supersymmetry transformation of a bosonic geometric tensor goes to a fermionic geometric tensor. So, and if you think about it, we have to do the same thing now for the fermions, because they have now extra S supersymmetry, and I introduce gates fields to them. But then if I look to the curvatures, then again, you can divide them into two types. Either you have curvatures where if you set them to zero, you can solve for the S supersymmetry gates fields, and then there's a conventional tensor, or it is a component where the gates fields drop out, and then there's a geometric tensor. And well, and so yeah, and indeed you can solve for all these gates fields except for a certain component, but that's okay. You don't have to solve for everything. These components just don't occur in the theory. So that is something we have seen before. So the conventional constraints are all set to zero. The fermions now, and now you take these bosonic geometric tensors we had. We had set them to zero, so under supersymmetry, they tells you that these geometric tensors are zero. That is still okay, that's more constraints, but it should stop at some point. Now, if you vary this, it goes back to the derivative of these bosonic geometric tensors, that's okay. But now the tricky point is it also goes constraints on, now we get also curvatures of the spin connections. Here we considered curvatures of the Vielbein and the three form. Now we get constraints on the omega. And the point is here, you cannot allow any constraint because these are the equations of motion. Remember, the Poisson equation was a singlet constraint on the boost. It was a trace. You don't want a triplet constraint because then really you lose the Poisson equation. Then it's not a Newtonian gravity anymore. And this is the part of calculation. Well, what we have seen is indeed it works like that, but this is the part with the work approach. We have not yet worked out the full constraints, but it looks like it's going to work. And then that's very nice. Now, to be sure that this is a consistent limit, what you can do now is, and that is gates fixing. Because, and in fact, this is a situation which we encountered in earlier work before, where we did a similar limit, except not in 11, but three-dimensional, and for particles, not membranes. And then we just had to clock the ruler and this vector field. And then we saw that one of the constraints we found on omega was that it was a flat space. It only worked for flat space. That enabled us to do these gates fixing conditions. The important thing is that you could gates fix away by Studebaker symmetries all the components of this vector except what we call the Newton potential. And then you solve all these constraints are solved for, and you can show that the theory reduced to Newtonian gravity in a flat background. And since it was supersymmetric, we also got a fermionic part of the Newton potential, which we call the Newtonian potential, and they nicely fit in a three-dimensional supermultiplet. And this calculation, which worked, it's really similar to what we are doing now in 11, but there are important differences because we have not a particle but a membrane, and we have these extra dilatations, and we have now a three form, but we checked already that the three form, again, because it has gate symmetries, that become Studebaker symmetries, it reduces to only a dilaton in the world volume direction. And well, again, this is, we are still busy doing that, but it looks like the answer will be that if you do the gates fixing, you get a simple multiplet which contains a Newton potential, which is the world volume component of the three form, a Newtonian potential, and this cell-Lagrange multiplier. You can't get rid of it, and I think you really need it also to realize supersymmetry. So this is a kind of funny small multiplet. This is, you could say, a little mouse which lives in this huge 11-dimensional supergravity beast, elephant, and which is self-consistent by itself. So you can calculate all the symmetries acting on these fields and check that they have a closed commutator algebra. So this phi, for instance, will now transform under Galilean symmetries, etc. It will be like in the bosonic case, and well, you can check this is so that's the final statement I make that hidden in 11-dimensional supergravity, if you take this limit, is this small multiplet which has a closed supersymmetry, algebra. But as I said, it's still to be confirmed, but this is how it looks like. Now, how much time do I have?
About 12.
What?
15 minutes, about 15 minutes.
So, that's the result so I'm rather confident, but it's not yet that we have put it on the archive because it really needs some further checks. Now, so the nice thing is that if I look to generalizations, now you could do similar limits for all the supergravity theories. To A, you just do by double dimensional reduction. To B is slightly different, but it should work in a similar way. We took the limit effect of the SL2R, of the SL2R duality, and something very funny happens because what you get is that you can't realize the SL2R on a single string. In the relativistic case, you have always a fundamental string and a Dirac-Brane, and they rotate in the SL2R. But here we find two different strings with opposite sign of the charge, and half of the SL2R rotates one string, the other half that string, and then there are SL2Rs which connected to strings. So you really need two strings to relate the SL2R. But not in the supergravity action itself. It's a matter of a sign change. Strings are sensitive for sign change of the charge, but in the action is not the case. And then you can realize this SL2R also in the non-relativistic case. But it is it's a different representation. All the fields transform in a rather funny way under SL2R. And to explain why they transform in that way, you have to use a piece of mathematics called invariant theory. This is an old piece, but you see you get kind of polynomial representation of this SL2R duality, but that works. And again, you have to use the similar tricks which I did in 11 dimensions. What's a bit annoying is that if you do heterotic supergravity, that there's an additional challenge. Then you do NS1 supergravity plus Yang-Mills, but then you have this famous Lorentzian-Simons term, and also you have a combination of Yang-Mills supergravity, and then we are still dealing with infinities which we can't tame. I'm definitely not saying it doesn't work, but we have to think more about it. It's more subtle here, because if you look to a sigma model representation, the Lorentzian-Simons term has to do with anomalies on the world sheet. So it's not quite that you have a nice second model coupling, which already involves the Lorentzian-Simons term, it goes more subtle. So this is something we still have to think more about. And I should also say that, like the way I approached membrane, you get membrane supergravity. This you can do also for other p-branes. For in 11H you also have a phi brane, and you could also take a limit adapted to this phi brane and take then the limit. It's not that each time you have a different gravity theory, it's just that if you approach an extended object, you see effectively a different gravity. That even applies to cosmic strings in real life. If you a Newton-Cartan gravity is adapted to a particle, but if you approach a cosmic string, you can approximate as an infinite array of particles. And if you take the limit to infinity, so the limit of the distance of particles to 0, then you really get this, you get string Newton-Cartan gravity with the potential which is only in transfers in the directions transfers to the cosmic string. Now I come to a thing which I must say I really don't know. I'm not 100% in control of it, but I think it's nice to discuss because I also have myself a few issues, and so oh wait a moment, sorry. And that is, and that I end, is, you see, there's something funny going on, because if you go back to 10 dimensions first, then you have this non-relativistic string, there's a sigma formulation done by these people here, and then you also can show, in fact, that there's an interesting connection between this non-relativistic string and what's called the discrete Lightning quantization of relativistic string theory. If you take, you can do the Boucher T-duality, but if you do the T-duality in the direction, because these are Wien strings, these non-relativistic strings, if you do the T-duality in the direction of the string, then you get the Polyakov string with a null isometry. You get something which people use for discrete Lightning quantization of relativistic string theory. And if you think about it, really what you do is that you take the usual Boucher T-duality in relativistic string theory, and at both sides you take R to infinity. At this side, R to infinity effectively is this non-relativistic limit I've been discussing. At this side, it becomes the null reduction, but the null reduction is always a bit funny. If, as Seiberg has shown, a null reduction is really the same as a spatial reduction followed by an infinite boost. So it's just also a limit. And if you do that limit, then you get this guy. So you really get a map between this and this you really can check in detail. So this we did in 10 dimensions. For instance, you really can, now you have the Boucher duality rules between this and this. For instance, you can look to waves and strings at that side and map them to waves and strings at this side. So for instance, the wave here in the relativistic string theory, it has a null direction. That maps to the Wien string in non-relativistic string theory. And if you take the string here, that's the funny thing, you would expect a wave here, but there are no waves in a non-relativistic theory. But what it happens, it becomes one of the unbound strings, which were discussed by these people. It's a solution of the equation of motions, it's half BPS, but it has not a physical equation of motion. It tells you that the spatial momentum squared is 0, which is exactly the Laplace equation for the Newton potential. So it's used in off-shell calculation of the amplitudes. That tells you exactly that this actually Newtonian gravity, instantaneous Newtonian gravity between the objects. But what is now, and I feel a bit embarrassed, is you see what is the confusion, and that also comes back a bit to what you were saying, that for me at least is confusing, is you see, this is called non-relativistic string theory, but in which sense is it non-relativistic? The question is, does it contain relativistic features? Because here, this you would naively say, well, this is a discrete likelihood. It is a relativistic theory. So in which sense does this know about non? So it's a very, very funny map. And the issue is a bit that, well, you see, discrete Lightning quantization is something, what people do is that they take the spectrum, they take the null reduction, and they take the momentum fixed in the null reduction, the P plus is constant. And then they divide the spectrum in Galilean blocks. And then they take the momentum states higher, and at the end they get the whole relativistic spectrum, but it's all divided in Galilean blocks. And if you compare these Galilean blocks, you get an identity. But the question is,
basically it's infinite momentum limit.
What? Discrete, yeah.
It's infinite momentum limit,
Yeah,
so
yeah.
you lose relativistic invariant when you take infinite momentum limit.
But, yeah.
It starts as relativistic,
Yeah.
then you go to
Yeah.
infinite momentum limit, and actually only what stays is a zero momentum guy.
So you would
Because
say,
that guy cannot scale.
yeah. So you would say the discrete Lightning quantization of relativistic theory is something non-relativistic.
I mean, exactly same way as left-hand side is not, because you can say left-hand side is relativistic because it starts as relativistic, and then you scale up, and when you scale up,
Yeah.
you are
Yeah.
introducing
Yeah,
the breaking down. So I think this is pretty similar on both sides.
Yeah, no, because that was my question also. Where are the relativistic and non-relativistic aspects of these two theories? Because we have here a map, but well, that's also what I thought. But if you talk with people somehow, that I would say also this is then at this level non-relativistic. And you compare also the
People are so
non-relativistic
many,
method.
they have many opinions.
What?
There are many people, they have many opinions.
Yeah,
It's
well,
okay, it's okay.
I will introduce you to some of these people, and it is a bit confusing, but that's also what I would think. Now, let me finish by saying that, so what I did in some sense is an uplift of this to M theory, because I have now, instead of wrapped strings, I have wrapped membranes, and so the wrapped membranes, they go to particle geometries in 9 dimensions, and on the other side, what I do is a null reduction and a spatial reduction, then also go to 9 dimensions, and they should be the same. And this is now I also go back to another remark what you say, is that, you see, if you do a null reduction of M theory, people never discuss the consistency with supersymmetry, because a null reduction is a constraint, because a null reduction means that the Killing vector squared is 0. You set a field to 0, but then that you vary it under supersymmetry. And the question is, how many constraints do you have? And in some sense, I've answered this question, because you get as many constraints here, because if you go to 9 dimensions here, you get the same thing. So, and I also got many constraints, but I claim they are closed. They lead to a Newton-Cartan gravity theory. So if you do a null reduction, you get many constraints, but my calculation indirectly shows that it doesn't kill the theory. You get a finite number of constraints, and it's all consistent under supersymmetry. But this question has never been addressed in the literature. People always do null reductions, and they forget to talk about the consistency with supersymmetry. But I think it works. And then you get a kind of map between wrapped membranes and a kind of discrete light quantization of M theory. So one final thing I would like to say is that the whole existence of the limit was based on fine-tuning of the coefficients in 11-dimensional supergravity. It really didn't work if you took any other coefficient. So it would be interesting to see, can you use this now also as a way to get information about high derivative corrections? Because if you add alpha prime corrections, can you take the limit? Well, again, I think that the enormous fine-tuning is not going to work unless the coefficients have special values. So you could maybe use the requirement of the existence of a non-Lorentzian limit as a way to get information about the coefficients in the alpha prime corrections. So that would be kind of interesting application.
By fine-tuning, you mean fine-tuning beyond constraint from 11 dimensional
of the coefficients in the action.
No, so the high degree return, for example, the leading high degree correction to what you wrote in M theory is the force coupling.
Yeah, for instance.
It has a full supersymmetric completion.
Yeah. And
are you saying the overall coefficient? Are you saying this procedure, constrain the overall coefficient?
Well,
or
also
the relative
coefficient.
I mean, relative, that's just a consequence of supersymmetry.
Yeah, but I get it now without supersymmetry. No, of course there are other ways, but I know, but I'm saying that also
this limit supersymmetry transformations change.
Yes.
You see, it is actually what Eric was discussing. I think is we know example where everything we understand, and this is not, of course, this one. This is very different, but spiritually and actually conceptually. Take supergravity, okay, and say I want to send mass Planck to infinity. It's a valid thing. It's a parameter, so you send it to infinity. So now in supergravity theory, metric is dynamical. There is a supersymmetry transformation of the metric and all this. But in this limit, you get rigid supersymmetry. Metric is background, it's not dynamical, right? But now supersymmetry transformations are completely different, right? Because you are going from the local supersymmetry of supergravity theory to rigid supersymmetry of supersymmetric theory, but in a card space.
Yes, background.
Right? That's the way actually to discover what some people want you to do, how to write the supersymmetric theories in the card backgrounds. You just take supergravity theory, take mass Planck goes to infinity. So what Eric is doing, I think, is taking parameters of a background, which you described very well, the turbine theorems there, and consistently everywhere taking the limit when one of these guys are scales to infinity. So if you follow probably step by step, you would discover that the supergravity transformations that you started with, so on, also are affected by this limit, and you will have a different transformations, and the action that you will get will be invariant under this new transformation.
Sure.
And everything goes fine, exactly like mass Planck goes to infinity.
Yes.
Because anybody who worked on, okay, our friend Peter Van Nieuwhof, I would ask, how can or Sergio Ferrara, how could that be that rigid supersymmetry has hyperkähler, whatever moduli space or something like that, and the supergravity theory, which is a quaternionic, right? How can these two be compatible? Answer is, when you take that mass Planck goes to infinity limit, lots of things change, including supersymmetric transformation. And that's what I think Eric just explained. No, am I right, Eric?
Yeah, the supersimple really, I even have
Yeah, I agree- I
field,
agree with that.
it's
I was just a
it's
little
completely
surprised.
different thing.
Yeah.
All I'm saying is that so that I didn't to take the limit. I didn't use super. All I'm saying is that in the action I had certain terms, and
Yes.
they really need to help each
I
other to
understand.
let work, and that gives me information
Yeah,
of
yeah.
these coefficients.
Yeah,
And I just wonder, can I use this?
Yeah, I
Anyhow.
understand. What I was trying to ask is, does it give us more information than we already know for the higher degree terms in the dimensional supergravity? That's what I'm asking.
Well, okay, I dare not thought about it.
So because we already know the structure from
But
supersymmetry.
only for R to the fourth, so it maybe not for higher order R's.
It probably constrains something if you have independent way of you see what this construction that Eric. Sorry, Eric, I'm answering for you. Is it okay? Can I answer this question?
Will you say it again?
Can I answer this question?
Yeah,
Would
I
you
forgot
allow
the answer
me?
was, but if you know a good answer to that question, then I should feel welcome.
No, I just wanted to say that the question is very good, of course, but answer probably is connected to the following part. You can't get more information just by taking the limit. If there is an independent way,
Yeah.
if there is an independent way to calculate some term
Yes.
in the limit, then it's probably constraints.
No, but that was so supersymmetry, of course, only tell you relations between terms in the lemma-dimensional supergravity at the same derivative order, right? It tells you relation between R to the fourth and C
But you're not your
wedge
overall.
I8, for example, but then it doesn't tie together R4 with R. What I was wondering here is whether what Eric is doing would give you relation between those in terms of different
Because
derivative
sometimes you have new parameters
not, right?
which are not fixed by supersymmetry. And this parameter from the R to the fourth is not by supersymmetry related to the parameter from the
First of all,
Einstein
Sorry,
term. The parameter from the R to the fourth
yes,
is not related to the parameter from the Einstein by supersymmetry.
it's not really
Yeah,
by
no,
supersymmetry.
yeah,
Yes,
yeah.
of
So-
course, yes.
Well, I can only guess, but perhaps it would be nice to see whether this way of doing it could lead
Yeah,
to
so
a relation. But I really,
That's what I was asking.
Yeah, no,
and
no, I
I'll be
understand,
surprised if this.
yeah,
this
but of
would
course
have-
it's a completely, well,
First of all, I would say that actually the R term and R square and R cube and all of them are related. They are related through the strict zone. It is just unique
Of course,
extension, right?
of course. And we know R
Now,
square, R
question
square
is,
is
question
zero.
is whether there is a simple principle. which
Yeah, yeah,
relates
yeah.
so
not
this is a kind of different way to look at it. That's all I'm
Yeah.
saying.
I think it's similar to what people. So there was activity. I remember this is because it was like last 10 years ago. Or something. People tried to write the super transformation in a card background. Okay, supersymmetry. This was a big activity. They would take this kind of card space, and then they would, and term by term, finding that this is. And I was once on a lecture on the beach at Simon Center Beach Club, and I asked, why are we spending so much time on this term by term building up and so? Can't we take just the M-Planck limit? And Nazi Zyberg said, yes, it's a correct answer. So it is like that. Okay, so you can go by term. So what you have to do in higher derivative terms also, you have to correct the super transformation.
Yes.
Okay, like they were doing. Or you can do like here, right? And then any calculation you do in before limit will lead to the answer after limit, which, as I said, separately you could have probably discovered otherwise. I think that's the answer.
Let me finish my seminar. I need 30 seconds to finish it.
Oh, sure.
Because it's the last one. So I would like to say that this is a kind of example of. So these days people look in many more examples of not only with supersymmetry but also without supersymmetry non-Lorentzian gravity theories in diverse dimensions. For instance, there's a whole field also in condensed matter where people use these things to couple to condensed matter systems, Newtonian gravity, the group of sonnets, etc. So it's just nice to see how all these non-Lorentzian structures, how they work and what they can do. And this is one more example then of, so you have a whole class now of non-Lorentzian gravity and supergravity theories in diverse dimensions, and it'll be interesting to learn more about them. That's it.
Have you looked at the possible ADS-CFT applications for,
Say it again?
possible ADS-CFT applications in this context?
Yeah. Well,
I mean,
that was
other
also one of my.
solutions.
That is. So usually people do non-relativistic holography. They take always special solutions of relativity, like Lipschitz space-time, Schrödinger space-time,
example,
any map
yes,
to non-relativistic CFT
Yes,
boundary.
yes.
The question is then, And that was one of the motivations, so I forgot now to mention it, that is also something like holography where you have non-relativistic gravity to build, and then, but then it's different, it addresses different kind of conformal field theories, different symmetries.
Yeah, but for example, just consider like a stack of M2 and you look at near horizon.
Yeah,
maybe
well,
some
so
similar...
we can go a long way in the sense of we can try to mimic what people did in the relativistic case, because these 2B supergravity, we can certainly calculate from deep range solutions, and we can see what happens. You see, on one side, I would say something should exist, because why? Because we know that there are these non-relativistic conformal field theories, and why could gravity not describe them? But there are some issues which makes you nervous, and one of the issues is that people always complain about is that in the relativistic case, there are always these black hole solutions which play an important role to describe CFTs at finite temperature. And now it's certainly true that standard Newtonian gravity has no black hole. If you take the limit of short, it goes to a naked singularity. That in some sense is a bad thing, but don't forget these are really different. This is not the standard gravity we have here. We have all these different foliations, membrane. So the question is, can you find a solution with the horizon? That would be very nice to see. And that I just don't know. So, but the nice thing is that we have now concrete things in our hand that we could investigate this matter. So at least we could try to make a statement. Is such a holography, yes or no? We are able to answer the questions now with the information we have, but I don't dare to give the answer right now. I just don't know. Some people say, no, never possible. Others say, well, you should look carefully. Because each time things change and happen and unexpected things. So one has to be careful. I have an open mind towards it. And whatever it is, I just want to know the truth. Isn't it? That's our task, to find the truth.
I already asked all my questions. I already asked all my questions.
Oh, okay.
Sorry, I interrupted.
No, that is good.
Yes, there are already many questions, so let's thank Eric again.